So it's definitely a good idea to write down or know formulas from geometry, area, surface area of shapes, of a sphere, and volume of shapes. I think spheres, cones, pyramids, and cylinders, and boxes, like, like rectangular boxes. Those are types of shapes that come up a lot. If you see those in your homework, then please, I think, go ahead and know those formulas or be able to write them down. Like the formula for the volume of a sphere, do you have that committed to memory, and do you need to? Like, I would write that down just in case it comes up. Let's see, other formulas from calculus that you would need. Well, I just want to remind you now, for integration formulas, we're really not looking at a lot of standard formulas. Most of this is ideas. So there's the idea of finding an antiderivative. This is definitely on the exam. And with antiderivatives, in general, you have to find some big F of x plus a constant. That's the general antiderivative of the function. And so I'm writing this down this way because I want to remind you that indefinite integrals is the symbol for antiderivative. If you see this symbol with no endpoints written in, then you know that we're talking about an antiderivative. That's what that symbol means. The integral is used to refer to the antiderivatives when you don't put in endpoints. Cool? Now for antiderivatives, there aren't standard formulas. These are all, you have your rules of thumb for differentiation. So your derivative rules, I'll say. In reverse. So like, the derivative of the natural log of t is 1 over t. So you know an antiderivative, or the general antiderivative of 1 over t is the natural log of t plus c. You know that the derivative of the cosine is negative sine. So you know that the antiderivative of the sine will be negative cosine. How do we know that? Okay, let's just do this example. If you know that the derivative of the cosine is negative the sine function, all right? And you want to know what an antiderivative of the sine function is. Well, we don't even have the sine function written down here. We're not in the place yet that we can ask what's its antiderivative. To find the antiderivative of the sine function, we need to first, all we have is the negative sine function is what I'm trying to say. We need to move that minus sign over here, and now we can ask the question. So now we know that the negative derivative of the cosine is the sine function. Therefore, that's the same thing as saying the antiderivative of the sine function. Okay, so now when I'm going to put, what I want to do is I want to put an integral symbol over here. What I want to do is do the same thing to both sides of this equation, right? So really what I want to do is to integrate this thing I'm just trying to use the rule from algebra that you do one thing to one side of the equation and you do the same thing to the other side. See? So I put integral symbols on there. But what happens? What happens when the integral collides with the differentials? When you see these two symbols come together, if you see them side by side, they cancel. They effectively cancel. All that's left is the minus sign, the cosine part, and the plus c part. What I'm trying to say is that over here, I just put the integral sign in, the integral and the dx. But over here, when I did that same thing, all of those symbols canceled out. And we're just left with the only symbols that don't look canceled out are minus cosine x plus c. So see, by adding that, by putting that integral sign in and all of that magic that happened on this side, all that happened from that was it cleaned up into a plus c. I'm just showing you the idea of antiderivatives, that you move back and forth between them. Because this equals that, then in reverse, this equals that. Derivative rules just work backwards to give you all of your antiderivative rules. And of those, there's really only one that is kind of its own rule. And that's the power rule in reverse. The power rule in reverse is the one that says that the antiderivative of x to the a, where a equals constant, that means it's not a function or it's of x itself. If that's a function of x itself, this is much more complicated. Is equal to, well, we take x and we do the power rule in reverse. So instead of subtracting 1 from the power, we're going to lift it by 1. And instead of bringing the power down, the old power down and multiplying, we bring the new power down and divide by it. And then, in order to finish the process, we have to put a plus c. That's what finishes this and makes it correct. Okay? So the power rule in reverse. This is one antiderivative rule that I think is worth writing down, because it's not always clear that you're looking at this rule when you first see the problem. For instance, I think that we saw a problem that asked us for something like the derivative. I can't remember exactly what it was, but I'm just going to put out there that it'd be something like, let's say, the square root of x to the 5th power. I think this was a problem in the homework. This isn't useful right away. This looks really confusing. It's useful, though, if you rewrite that, of course, in the function theory way using exponents. X to the 1/2. Exponents make roots much easier because now you can see you just need to use exponent rules. So this is going to be x to the 5/2 power. And now it's in the form to use the power rule in reverse. You're going to take 5/2 and add 1 to it, divide by that new number, plus c. I'm not even going to do it. That's an example of how you need to put something in the form to see that the power rule in reverse will work. And that's why I'm kind of giving you this example. Now, let's think. Other specific formulas from this section. Again, there aren't many. It's all about ideas. Most of the formulas come from earlier in the semester, and truly, almost all the formulas in this class come from pre-calculus, geometry, and algebra. Okay, antiderivatives are just derivatives in reverse, so you just have to know about derivatives. Okay. Okay. If any of you need to leave now, I see it's getting to be the end of class time. Of course, you're welcome to go. Thank you for coming today. Other things that you would need to know is the fundamental theorem of calculus, part 1. That says that if you take the derivative of a function, check my lecture, by the way, from last week. It's on ESE. Take the derivative of an integral, and remember that the variables inside the integral cannot be the same variable outside the integral, because x is the upper endpoint of the interval that you're integrating over. Remember from my lecture on the fundamental theorem of calculus from Friday. Check that if you don't know what I'm talking about, because I think I gave a nice example of how to think about this. But what happens? What happens when the derivative symbol collides with the integral symbol? When you see these two things together, students, when you see them come together, just like in the last case, they cancel, just like square and square root. They cancel in the sense of being operations. This symbol and the integral symbols that are on either end of the function, they like have a laser battle. All that's left is the function itself. All of the walls are destroyed, except for x pops down inside there. Pops down inside the function. However complicated that function is, as long as it makes sense, and we need the constant, this point a, x equals a, this endpoint needs to be in the domain of f of x, of f. We'll say f of t. I'm just saying nothing makes sense in math if you're writing down stuff that's not in the domain. So I'm just saying that number down there has to be in the domain of the function. And presumably your x value is as well, that you plug in finally at the end. Cool? Okay. So you're like, I understand that A has to be in the domain, right? It has to be conceptually there for this to make sense. We can't talk about functions without talking about domains. But where did A show up over here? Did it matter if that was 1 or 2 or 3? Did it even matter in the final calculation if it was in the domain? It really doesn't. It doesn't practically matter what that lower bound here is, because in the end it disappears. You'll see that from the proof of this that we did last time in class. That's on ELC. So easy. Whatever function is inside the integral, in this setup where you have a derivative kind of colliding with the integral symbol, whatever function's inside there is freed. It's freed up. It comes out. And x kind of like hops off from above the integral and in there. And they're like, we're out of here. That's the way I like to think about it. They escaped. The function was trapped. X was trying to help out. Derivative comes along, smashes the wall, I guess, open, and they escape. It's some sort of a like breakout, prison breakout type scenario here. Okay, that's the fundamental theorem of calculus part 1. Now there's a trick to that, because sometimes you're, here's a tricky part, caution. When using the fundamental theorem of calculus, what if your endpoint's on the bottom and not on top? We can't use the fundamental theorem part 1 because it's not in the right form. You have to tweak this to put it in the right form. X has to be up top. X can't hop down off of the top of that thing and jump in here and like drive away. That can't happen. It's down there. This comes, smashes the wall open. F of T's like, I've got no driver. X is all like, I'm underneath the rubble. That's so much more trouble. Hey, that rhymes. Okay, what you need to do is flip the integral upside down. You want this. You want this form. We're going to make those variables really small over there. Sorry for that. That says f of t dt. You want this, but when you flip the integral upside down, you pick up a minus sign. That's what happens when you reverse the order of the integration from top to bottom. So you're going to get negative that. And now you can go ahead and they crash through the walls. F comes out. X hops down inside of it, but it's got a minus sign. They drive off. They're free. They're unjustly imprisoned in this particular film. Okay. Cool. Okay, that's my action movie version of antiderivatives and the fundamental theorem of calculus part 1. You all buy that? It's so easy. See, you just took the function out from inside the integral and popped x in it, and you're good to go. There are a few more complicated situations, but really noting that you need to flip the thing upside down is really important. You can't use the rule if you don't have the right form. Kind of like with L'Hopital's rule. You have to put it into the right form before you can apply that rule. Now, this rule, these are some integral rules. Is one of a few very simple rules about integrals that are very natural. For instance, integrals also, whether they're definite or indefinite, definite or indefinite integrals, they all follow rules like this. Well, there's a constant multiple rule. If you have a constant times a function, 2x squared, for instance, that's the same as taking the constant outside and just taking the integral of x squared or whatever, and then multiplying by the constant in the end. Cool? Constant multiple rule works just like it does with limits and with derivatives. We get a sum and difference rule. So if you have a function that's made up of a sum or difference of other functions, like polynomials are like that, x squared plus 3x, that's a sum or a difference. So this is your function is made up as a sum or a difference. Well, that just splits up easily into Just like with limits and with derivatives, a sum or a difference of those integrals. Same for both definite and indefinite integrals. So you have these rules that are very familiar for integrals as well. Is there a product rule? Is there a quotient rule? Is there a chain rule? These are things for you to find out in calculus 2. I mean, of course, there are rules that are like those rules in reverse, but because of all that plus C business and some of this other stuff with the fundamental theorem of calculus, it's just a little more subtle, but it's not very much more subtle, and it's just as easy as doing these kinds of things. The other two rules that are like this to note, where'd my eraser go? I always drop it, and it's the same color as my porch. Okay, here we go. Another couple of rules about integrals. Let's see. Well, we have that you can take an integral from A to B. I went over this last time too. And if you put a point C, so if A is less than C is less than B, right? You take a point C that's in between A and B. You can split this integral up into one from A to C, and then again from C up to B. So you can split it. You can split your domain, and you can split your interval into two sub-intervals. And similarly, you can split this up. And I drew a picture of that last time. It's a rule. I don't know if these are rules for your cheat sheet, because they're so easy. But it wouldn't hurt to put it down if you're in doubt. And let's see. And then the other big rule like that. This is really useful, okay? It's really useful. It's often very easy to split an integral up at a point. That makes it suddenly look much easier, okay? It's just really easy. Here, let me just give you an example of why you'd care about that. Let's say you have the function y equals sine x. Okay? Notice that the function's periodic. Every single hump above the line is exactly the same as the hump below the line, but it's positive. Every area above the line is equal to every little hump area below the line, except for that it gets a minus sign when it's down below. So if you want to find the integral from A to B, it'd make a lot of sense if you only found the integral from C to B of the sine function. And then you noted that this is going to be the same thing, but negative. C to B. I'm just saying you take this integral, flip it upside down, it gets a negative value. You add those together. Well, of course, when you add plus and minus something to itself, it's going to be 0. And so you can instantly see by splitting that into two halves. They have the same shape, they have the same area. The bottom one gets a minus sign. So that integral is going to end up being 0. And you can do that without computing it. You can just compute one piece of it and kind of look at it. I'm just saying this is an example of splitting the interval and then just looking at part of it to find out information about the rest. And I think the other useful integral rule that you need to know besides all of those is the one that we just did, which is the average value of the function y equals f of x on the interval a to b, noting that this interval has to be, it could be also an open interval with round brackets. It has to be in the domain. And that is equal to, amazingly, the area under the curve from a to b divided by the length of the interval, b minus a. So crazy. And then of course, using the fundamental theorem of calculus, part 2, which I'm about to give, we can transform this further. That's the average value. And how you're going to compute the integral part of this comes from the fundamental theorem of calculus part 2. And it is as follows. Remember, part 1 says that derivatives and integrals cancel, so to speak. Part 2 is about computing areas. The fundamental theorem of calculus part 2 says that the area under the curve from A to B, which is what that symbol means, the definite integral. Gosh, it's so beautiful and easy. All you have to know is an antiderivative, big F of x, and then evaluate it at the two endpoints, at the left-hand endpoint and the right-hand endpoint. And remember from my lecture on Friday that this symbol is a new way to write subtraction. We're going to use this a lot in calculus 2. What does this say? Well, it says, you know, the antiderivative is this, but this tells us you take whatever function is there, you put in the top value. It matches with that one. And then you go, this line is like subtracting. You slide down the line instead of a minus, and then you take the bottom value and plug it in. Cool. That's the fundamental theorem of calculus part 2. Note there's no plus C. No plus C. Really, plus C doesn't factor into either of the fundamental theorem of calculus theorems, does it? Plus C has to do with antiderivatives, indefinite integrals. When you're doing the fundamental theorem of calculus, you're always looking at definite integrals, even though one of them might have x in it. This is a very beautiful and surprising theory. All of these formulas look so simple and so familiar. This resembles just it resembles the writing down the length of the interval b minus a itself. And that big F is an antiderivative. We've worked through all of this theory, telling us what different functions, how they relate to each other into their graphs, the areas and the curves of the graph. In the end, though, when it comes back down to it, it all looks like very simple and familiar formulas. And this is why I always have said from the beginning of the semester, it's not calculus that's hard. Calculus is actually really elegant when you see it all bundled together. It's simple. What's really, really hard is the algebra that's along the way. And you've already learned that in the past. You just have to practice it over and over and over in this theory. I think that is all of the useful formulas I can think about, except for just the stuff that you need to build confidence. And for instance, useful formulas from the previous exams, I'm sure will still be useful in the final.